to calculate the multiplicity for some number of permutations or combinations is useful primarily if each one of those different arrangements of some objects is equally likely as all the others, and then that allows us to calculate the probability of some permutation or some combination of those objects. But one way that molecules and chemistry problems are very unlike dice and coins is that different outcomes are typically not exactly the same probability as each other. Every outcome on a roll of a die is exactly the same, but different conformations of a molecule or different energy levels in a molecule don't all have the same probability of occurring. So we need to be able to understand what happens when the probabilities of each individual event are different from one another. So to consider that, we'll need to talk about this binomial probability distribution. But let's start by considering the case we do understand fairly well at this point, which is a case involving coins. So let's say we flip 10 coins, come up either heads or tails in each of 10 flips, and let's say we want to know what's the probability that we get 5 heads and 5 tails. So just as an example, so that's the real question we want to know the answer to. As a warm-up, let's say I'll just write down some particular combination of heads and tails, 1, 2, 3, 4 heads, 1, 2, 3, 4 tails. So let's say here's a particular arrangement of 5 heads and 5 tails. What's the probability that if I were to flip 10 coins, I would get a heads and then a tails and then a tails and then a tails and so on in exactly this pattern? Notice that that's an and problem, heads and tails and tails and tails and heads in that pattern. Those events are independent from one another. So I can say that that probability is the probability of heads times the probability of tails, but that's exactly the same as the probability of heads. So it's 1/2 times 1/2 times 1/2. Every one of these outcomes I had a 50-50 chance of seeing the exact thing that I got. Since I flipped the coin 10 times, that's 1/2 to the 10th. So that particular outcome has a probability of 1/2 to the 10th. That's not the same as asking what's the probability that I get 5 heads in any order and 5 tails in any order. If I go back to that question, probability of getting exactly 5 heads is the probability of getting any one of those events multiplied by the multiplicity. How many ways are there of getting 5 heads and 5 tails? So that's where the binomial coefficient comes into play. So each one of the events has probability 1/2 raised to the 10th. The multiplicity of getting 5 heads in 10 coin flips is 10 choose 5. How many ways are there of choosing which 5 places to put the heads in this list of 10 outcomes? So as a number, I won't write out the factorials, but 10 factorial divided by 5 factorial divided by 5 factorial, that number is 252. 2 raised to the 10th power in the denominator, that number is 1024. So roughly 25% of the time, we'll get 5 heads and 5 tails. So maybe pause for a minute and think about that. If I had asked you ahead of time, if I flip 10 coins, what's the most likely outcome? Is it going to be 5 heads and 5 tails or 1 head and 9 tails? You're probably going to think 5 heads and 5 tails is most likely because that's 50-50, but only, and it is the most likely of all the individual outcomes, but only 25% of the time do I get exactly 5 heads and 5 tails. Getting 4 heads or 6 heads is not too unlikely either. But so that's how to do this problem. If we know that each one of these outcomes is exactly as likely as the other, heads is as likely as tails. Let's think about the more interesting problem now. Let's suppose our coin isn't fair. Let's suppose it's not a 50-50, whether it's heads or tails. So as a different problem, let's suppose the probability of getting a heads is 60%, and the probability of getting tails is the remaining 40%. So I have an unfair coin. So that's not super interesting when we're talking about coins, but that does begin to become interesting when we start talking about molecules, because that begins to allow us to ask questions like, what if I have a molecule that has a 60% chance of being cis and a 20% chance of being in a trans conformation? So thinking about it in terms of coins, however, we can say, what's the probability that out of 10 coin flips, I get 5 heads and 5 tails with this unfair coin. I think about the problem in the exact same way. It's the probability of any individual outcome. Let's take this outcome, for example. The probability of heads, tails, 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 heads, tails, heads, heads, tails, heads. But now instead of 1/2 for each outcome, I've either got a 60% or a 40%. So the so it's still the probability of any one of these outcomes multiplied by the multiplicity, the number of ways that outcome can occur. The probability of one of these outcomes, let's think about this one. So probability of a head, that's 60%. I want to multiply that by the probability of tails, that's 40%. And then tails, I'm going to have another 40%, another 40%, a 60%, a 40%. When I multiply all these together, I'll have 0.6 showing up a total of 5 times. I'll have 0.4 showing up a total of 5 times. So in the end, I'm going to have 0.6 and 0.4 each multiplied by each other 5 times. That's the probability of getting this particular arrangement of heads and tails. But notice, it doesn't matter what order I multiply those together in. That's the same as if the heads and tails were in some other arrangement. As long as there's 5 heads and 5 tails, this is going to be the probability of that particular outcome. And I still have to multiply that by the ways of the number of arrangements, the multiplicity, 10 choose 5. So what's changed in this version of the problem from this version of the problem is not how many ways I can distribute 5 heads among the 10 outcomes, but in how likely each one of those outcomes is. The heads have become more likely, the tails have become less likely. Overall, the overall probability has changed. And if I just skip the math, and write down what the calculator tells us, 0.6 to the 5th times 0.4 to the 5th times 10 factorial over 5 factorial over 5 factorial. That works out to be 0.201 roughly. So there's only about a 20% chance of getting half heads and half tails for my unfair coin. It's a little less likely than it was before because the coin is no longer a 50-50 coin. But the important thing is now we can do a calculation like this regardless of what the probability is of each individual outcome. In the general case, this binomial probability distribution that we're talking about, if I want to know, let's say I have event number A has some probability of occurring, some different event B has probability everything else. So 60-40, 50-50, doesn't matter, but those two numbers have to add up to 1. The interesting question that we can now write an answer to is, if I try something n times, what's the probability that little n of them come up with the result A? Then that's just, we've worked 2 examples of this so far. That's going to be the probability of one outcome times the multiplicity. Each one of the individual outcomes, I have to get A little n times, by definition. That's what I'm asking about. Each time I get A had a probability P. I get the other option B, that happens the remainder of the times, big N minus little n, and the probability of that happening each time was 1 minus P. So these things together are like the 0.6 to the 5, 0.4 to the 5. That's the probability of any individual outcome, and I still need to multiply that by the number of ways of getting little n out of big N options, so n choose little n. So this probability of seeing outcome A little n times is just the probability of it happening once raised to the number of times it happened, probability of it not happening raised to the number of times it didn't happen, times this multiplicity. So that's what we call the binomial probability distribution. Notice, be careful with the terminology here. Remember that this thing, big N choose little n, we called that a binomial coefficient. This probability, p to the n, 1 minus p to the n minus n, times a binomial coefficient, that thing is called a binomial probability distribution. So there's some possibility of getting confused between those two terms, but one is talking about a probability, one is talking about a multiplicity, a count of the number of ways something can happen. Keep those two terms in mind. As our last example, we'll do an actual real bona fide chemistry example now. Let's go back to our butane example, which we know has not trans, but anti, if we're using proper terminology. So a butane molecule has a 68% chance of being in the anti conformation, and then 0.32 is the probability of being in either one of the two gauche conformations. So let's ask the question, let's say I have 20 butane molecules, and I want to know what is the probability that out of those 20 molecules, 6 of them are in the gauche configuration. So collection of 20 butane molecules, I want to know, I might have all 20 in the gauche conformation, I might have none of them. I want to know what's the probability that 6 of them are in the gauche conformation. That's exactly the type of problem we use this equation for. Probability that 6 of them are in the gauche configuration out of 20 different molecules. That's going to be probability that one of them is gauche, 0.32, raised to the 6th power. That's how many of them I want to be in the gauche conformation. Probability that they're not in the gauche conformation, 0.68, raised to the 14th power. That's the number that are not in the gauche conformation. And then I multiply that by the multiplicity, 20 choose 6. So we clearly need a calculator to solve that, but if we plug the numbers into the calculator, 0.188, or about 19% of the time, we find that our collection of 20 butane molecules will have 6 of them that are gauche. So that's beginning to sound like problems that we couldn't possibly have tackled without some understanding of probability, and it's also beginning to show why these are relevant chemistry. Probability questions are relevant for answering questions about chemistry. The one thing that might occur to you to wonder at this point is, what if we have more than just two conformations? If I don't just have anti and gauche, but if I want to consider gauche plus or gauche minus or anti, or if I have a molecule with lots of different energy levels or lots of different conformational states, then using the binomial probability distribution isn't going to be enough. So the next video lecture will help us begin to tackle what to do if we have more than two options to consider.